In the last lecture, we learned about how to go from the soup in the early universe of particles and radiation bouncing into each other to figure out what would be left over at late times. How to go from very, very high temperatures to very, very cold like we have in the universe right now. In this lecture, we're going to give an example of that process, perhaps the most important example that we actually have data about in the universe right now. That's the example of the light elements. We have the universe, when it was about 1 minute old, acting like a nuclear reactor, turning individual protons and neutrons into helium, lithium, deuterium, other light elements, and today we can observe the amounts of helium, lithium, and deuterium from the early universe. We can make predictions on the basis of our understanding of cosmology and our understanding of particle physics, and test those predictions today to see if we correctly understand what was going on in the very earliest moments of the universe's history. So this is a fairly specific lecture. We're not going to talk about generalities anymore. We're going to dig into some very precise quantities, but it's worth the effort to follow what is going on because the payoff is enormous. Compared to talking about dark matter and dark energy, it can seem kind of pedestrian to talk about nuclear physics, something that, 50 years ago would have been the sexy hot topic, but now we understand pretty well. But the point is, Big Bang nucleosynthesis, as it is called, gives us our best empirical handle on what was happening at the first moments of the universe's history, and from that handle, we can infer things not only about what was going on back then, but what is true right now. In particular, Big Bang nucleosynthesis provides us with a very believable and absolutely comprehensive measurement of the total amount of ordinary matter in our current universe. The ordinary matter, the matter from the standard model of particle physics, the actual mass density of that stuff comes from protons and neutrons. In an atom, in a molecule, in this table, or in me, most of the mass, most of the energy is in the atomic nuclei, in the protons and neutrons. And nucleosynthesis is intimately involved with exactly how many protons and neutrons are lying around. For a different number of protons and neutrons, you would get a different prediction for helium and lithium and so forth. So the results of Big Bang nucleosynthesis tell us that the amount of ordinary matter in the universe is about 5% of the critical density. The critical density is the density of stuff you would need to make the universe spatially flat. Now, we don't know ahead of time that the actual total density of the universe is the critical density, but we can measure densities that we observe in terms of the critical density, and Big Bang nucleosynthesis says that protons and neutrons are about 5%. But we've already said that the total amount of matter in the universe, the amount of stuff that is accumulated in galaxies and clusters of galaxies, is something like 30%. That's why we know that not only is there dark matter, but the dark matter is something new. The dark matter is something different that is not ordinary stuff, as hidden as it may be. So the goal of this lecture is really to convince you of our understanding of that chain of logic right there. So we're going back to about 1 minute after the Big Bang. Again, we don't know what happens at the Big Bang itself, but using the Friedmann equation of cosmology, using our understanding of general relativity and how the curvature of space and the expansion of the universe responds to the energy density of the universe, we know what the temperature was about 1 minute after the Big Bang, or even 1 second after the Big Bang. What was going on back then? We had free protons and neutrons, and those free protons and neutrons couldn't join together to make atomic nuclei because the temperatures were too high. But as the universe cools, the temperature lowers enough so that a neutron and a proton can join together and stick together. Now, if you had a bunch of neutrons and protons at a low temperature, and you let them go to their lowest energy state, you let all the neutrons and protons transform into the state that they really wanted to be in, they would all be in the form of iron. Iron is the configuration of protons and neutrons that is the most stable thing. If you take an iron nucleus and you break it apart, the stuff you break it apart into will always have greater energy, whether it's smaller things, no matter how small they are. Likewise, if you take a heavier element than iron and break it down into iron, you will release energy. That's how nuclear reactors work. You can either take much heavier elements and have them undergo fission, coming closer to iron, like uranium or plutonium breaking into smaller nuclei, or you can have fusion, where you have tiny little nuclei going towards iron. So if the universe lasted an infinite amount of time and cooled off very, very, very gradually, it's easy to predict what the outcome of Big Bang nucleosynthesis would be. All of those protons and neutrons would turn into iron. The reason why that doesn't happen is because there's not enough time. The universe is expanding quite rapidly. So on the one hand, the temperature is going down, so it becomes possible for nucleons to stick together in nuclei. But on the other hand, the density is also going down. Because that density is going down, the frequency with which different atomic nuclei bump into each other becomes less and less frequent, becomes less and less large. So because they don't interact with each other, they can't fuse, and we don't go all the way to iron. We're stuck with helium and the other light elements. So let's run the movie backwards. Let's start with our universe today. Let's ask what happens when the universe was smaller and things were closer together. It's extremely analogous to taking a bunch of stuff in a piston and just compressing the piston. That compression of the piston is very much like shrinkage of the universe as you go backwards in time. So what happens is, of course, things get pushed together, the density goes up, but as you push a piston in, the temperature of the stuff inside the piston goes up because things are banging together more and more frequently. So the temperature goes up, the density goes up, and the temperature, as we've said before, is basically the kinetic energy of every particle, the average amount of kinetic energy. So today, the temperature of the universe, by which we mean the temperature of the relic photons in the cosmic microwave background, is about 3 Kelvin. A Kelvin is a set of degrees, just like Celsius degrees. 1 Kelvin degree is equal to 1 degree Celsius, but the 0 point of the scale has been moved so that 0 degrees Kelvin is the lowest possible temperature that exists. It's the temperature when the kinetic energy of everything is absolutely 0, so it's called absolute 0. It corresponds to about minus 270 degrees Celsius. So today, the universe is at about 3 degrees Kelvin. The Earth is at about 300 degrees Kelvin or something like that. The universe, in other words, is not in thermal equilibrium. The temperature is different from place to place. So as we take this universe, with the photons today being 3 degrees Kelvin, and we squeeze them as we go back in time, the temperature goes up. The temperature goes up inversely to the squeezing. So when the universe was 1/1000th its current size, the temperature was about 3000 degrees Kelvin. That's when the microwave background was formed. When the size of the universe was 1/1,000,000th of the size it is today, the temperature was about 3 billion degrees Kelvin, and that's the era of Big Bang nucleosynthesis. We can also tell you what times these correspond to by using the Friedmann equation. The Friedmann equation tells you that recombination, which is the moment when the microwave background was formed, is at about 380,000 years after the Big Bang. 1 minute after the Big Bang is the time of nucleosynthesis, the time when the temperature was about 1 billion times higher than it is today. In that era, the universe was not dominated by matter and dark energy like it is today. Dark energy, as we'll talk about later, has an approximately constant density as the universe expands. Matter dilutes away in energy as the universe expands because the density of particles goes down. But radiation has a density that goes down because the number of particles goes down, but also the energy per particle goes down as particles get redshifted. So of the 3 kinds of energy, radiation goes away the fastest as the universe expands. Contrary-wise, as the universe contracts into the past, the radiation goes up the fastest. So even though today radiation is a small part of the energy budget of the universe, at early times it was the dominant part. The early universe was radiation dominated. The things that were making up most of the energy budget of the universe were photons and neutrinos, light particles moving close to the speed of light. So when the scale factor was about 1 billionth, the universe was very, very hot. The reason why that's an especially important time is that the universe was hot enough that individual atomic nuclei could not survive. The temperature of about 3000 Kelvin at a scale factor of 1/1000th is the temperature at which atoms cannot survive. So electrons are torn from their atomic nuclei, but it's at 3 billion degrees Kelvin that individual nuclei cannot survive. Even if you had some atomic nucleus for oxygen or carbon or iron or whatever, back then the temperature was so high that the protons and neutrons would just be torn apart. So at times less than a minute after the Big Bang, at temperatures more than 3 billion degrees Kelvin, you didn't have any atomic nuclei. You had individual protons and neutrons. Before even that, you didn't even have different protons and neutrons. When the temperature was high enough, they were dissolved in their constituent quarks and gluons. But by 1 second or 1 minute after the Big Bang, you certainly did have protons and neutrons. They kept bumping into each other. This picture shows you a schematic picture of what happens through the thermal history of the universe. As you go from the very earliest times when the temperatures are very high, a series of transitions occurs as the temperature goes down. Well, the one we're talking about today is the one where you make the light elements. So let's start our starting point at about 1 second after the Big Bang. You have protons and neutrons going around, and 1 second is chosen because not only do you not have atomic nuclei, but 1 second is before the protons and neutrons have frozen out. Remember that freezing out is the moment when particles stop interacting with each other, that the rate at which things happen dips down because the densities become too low. At times earlier than 1 second, protons and neutrons were interacting with the surrounding plasma. What that means is that neutrons and protons were being created and destroyed all the time. They were not in a total quark number 0 state. There's more protons and neutrons at that time than there are antiprotons and antineutrons. Otherwise, they would have all annihilated away. There's some net baryon number lying around for reasons that we don't completely understand due to some unknown process of baryogenesis. But they're there. The forms they want to take are protons and neutrons. So when we say they've not frozen out, what we mean is that protons and neutrons are converting into each other very rapidly. So we talked about the process of a proton bumping into an electron and making a neutron and a neutrino. That can happen if the energies are high enough. So what we're saying is when the universe was less than 1 second old, the energies were high enough. Neutrons would interact with neutrinos to make protons and electrons, and vice versa. Protons and electrons would interact with each other to make neutrons and neutrinos. So everything was in equilibrium. And the thing about equilibrium is you have more light particles than heavy particles. The heavier a particle is, the lower its abundance is going to be because they're harder to make. So we know that the proton, for example, is a little bit lighter than the neutron. So when you can convert protons and neutrons back and forth rapidly, you will end up with more protons than neutrons because the proton is lighter. It's easier to have it around. So in fact, if you run the numbers, if you plug in the equations, what you find is that at the moment when protons and neutrons do freeze out, when these weak interactions that are converting from protons into neutrons and back again slow down so much they don't happen anymore, that's a moment when you have about 1 neutron for every 6 protons. I can't derive that for you in real time. That's what comes out of the equations. You have about 6 protons and 1 neutron for every 7 baryons lying around. So then what happens? This is the time at which you've frozen out, so protons and neutrons don't convert anymore. They just sit there, except of course the proton really does just sit there. Nothing happens to the proton, but the neutron isn't stable. Neutrons decay. The decay rate of a neutron is that it has about 50-50 chance of decaying once every 10 minutes. Now we're talking about timescales. The universe is only a few seconds old right now, so not many neutrons decay away. But between 1 second and 1 minute, some of the neutrons will decay away. The lifetime is 10 minutes, so most of them will be around, but some of them will go away. So by the time we've reached a moment, about 1 minute after the Big Bang, you went from having 1 neutron for every 6 protons to having 1 neutron for every 7 protons. So that's a number worth remembering. We're going to put that number to good use. We have 1 neutron lying around and 7 protons. The time is about 1 minute after the Big Bang. The temperature is about 3 billion degrees Kelvin. So what's so special about that time? That time is when the energy is low enough, the temperature is low enough that you can start to form nuclei, that you can start taking protons and neutrons and they can stick together and not be continually dissociated by bumping into other particles. So it's worth pausing at this moment, at this important moment in the universe's history, to emphasize that we're assuming a lot. We weren't there at the Big Bang or 1 minute after. We weren't looking at what is going on. How do we know all of these things we're saying about there's 1 neutron for every 7 protons, it was 1 minute after the Big Bang, the temperature was such and such? The way that we know is we never know for sure. We have a theory. We have the theory of general relativity. We have the Friedmann equation for the expansion of the universe that we've derived from general relativity. And we use that theory plus particle physics, plus the Standard Model, to make a prediction, to go from what we see today to what the universe must have been like. But we're not satisfied with making a prediction. We're now going to test it. We're going to say, if the universe were doing that, certain things should be true today. And so we're going to check it. So because those things will turn out, in fact, to be true today, we are pretty confident that we understand what the universe was doing 1 second or 1 minute after the Big Bang. So what happens? The temperature is now dipped down low enough that we can make nuclei out of protons and neutrons. So of course, you start with individual protons and neutrons, and you make the nuclei step by step. It's not going to happen that a whole bunch of protons and neutrons come together all at once to make one heavy nucleus. Particles will interact with each other one by one. So the first thing that can happen is a neutron and a proton can come together to make a nucleus of what is called deuterium. Deuterium is heavy hydrogen. It's one neutron and one proton in a certain atomic nucleus. Now that's easy to describe, but in fact, a deuterium nucleus is very fragile. So this slows down what you might have thought would be the process of nucleosynthesis, because you can make a deuterium nucleus, but it's so fragile they keep getting disrupted at this early time, high temperature in the universe's history. But the temperature is dropping bit by bit, continually going down, and what happens eventually is that two deuterium nuclei can last long enough to bump into each other, and they make a nucleus of helium. Helium has 2 protons and 2 neutrons, and helium is sticky. It is very robust. It is not very fragile. So once you make the helium, it stays there. So basically what happens, we start with 1 neutron, 7 protons, or if you double the number, 2 neutrons and 14 protons. What happens is basically every single neutron that you have lying around goes into a nucleus of helium. So those 2 neutrons and 14 protons become 1 helium nucleus and 12 protons. The helium nucleus has 4 particles in it, 2 neutrons and 2 protons, and you have 12 protons lying around. So 25% of the mass that you started with has now become helium. 25% of the baryons, of the total number of protons and neutrons, are now stuck in a helium nucleus. What you would like to have happen next, if you could just keep at that temperature forever, is those helium nuclei would stick together. You would start making carbon and oxygen and heavier elements. But what actually happens is the universe expands, so it doesn't happen. The helium just gets stuck there. So realize that this statement that I'm making with such confidence, of course, depends on details of what was going on 3 minutes after the Big Bang. It depends on the expansion rate of the universe. If the expansion rate of the universe were much slower, then you would have time to go from helium to heavy elements. In the model that we're working with, in the theory of general relativity and the Friedmann equation, you end up with almost all helium, about 25% by mass. You can do better than that. Besides the fact that you get 25% helium, you get trace elements that contribute just a little bit. Not all of the deuterium is sucked up into helium. There's some little bit left over. Not all of the helium nuclei stick around by themselves. Sometimes a helium nucleus will take on other little particles and perhaps become a nucleus of lithium. Lithium-7 has 3 protons and 4 neutrons in it. It's another light element. You can also have helium-3 with 2 protons and 1 neutron. So in other words, primordial nucleosynthesis takes individual protons and neutrons, and from that makes a whole bunch of helium, all the helium it can make, plus trace abundances of deuterium, helium-3, and lithium. In particular, it does not make anything heavier. It does not make carbon, oxygen, iron, all the stuff that is very important for our lives. So when this theory was first being invented, it was in the late 1940s, actually. It was in 1948 when the first paper on primordial nucleosynthesis was written by George Gamow and Ralph Alpher, and they were trying their best to make all of the elements that we know in the Big Bang. They were trying to make all the heavy elements. They eventually realized it didn't quite work. But they did realize they could make helium very efficiently, and the observations in 1948 weren't very good, but the predictions that Gamow and Alpher made fit very well with the observations that helium actually existed. This was the first quantitative thought that we could extrapolate our knowledge from the current universe all the way back to moments after creation. So Alpher was actually a graduate student of George Gamow's at the time. This work was Ralph Alpher's PhD thesis. His PhD thesis defense was attended by 300 people from the Washington, D.C. area, and the Washington Post had a front page story the next day, "Universe created in 5 minutes." My PhD thesis did not appear on the front page of any major daily newspapers, but it's a nice thing, I imagine, when that would happen. However, Alpher was not always happy with how things turned out because his advisor, George Gamow, was quite a practical joker. So when they submitted their paper by Alpher and Gamow, he added the name of Hans Bethe into the middle of it so that the author list read Alpher, Bethe, Gamow. That was a joke that's supposed to sound like alpha, beta, and gamma from the Greek alphabet. He didn't even tell Hans Bethe, who is a famous nuclear physicist, and he also didn't tell Ralph Alpher, who was the lead author on the paper. Alpher was upset because he was going to lose some credit because now he had 2 very famous collaborators, not just one. Nevertheless, we now have a theory of where the heavier elements came from. We know that the heavier elements were not born in the Big Bang. The heavier elements are born in stars. They're both created while stars burn. Our sun right now is creating carbon and oxygen. And then they will be scattered when the stars explode in supernovae, and the supernovae will at the same time make even heavier elements. The very heavy elements, gold and plutonium and uranium that we see in the universe, are created not in the centers of stars, but in the actual process of the explosion of the supernova. So what we want to do to test Big Bang nucleosynthesis, we have a set of predictions. We have 25% helium, roughly. We have trace amounts of deuterium, lithium, and helium-3. The problem is the late universe is spoiled by all these supernova explosions. There's more and more elements processed by stars. The abundances we see today are not the primordial abundances. What we want to do then is to take observations of pristine parts of the universe, observations of parts of the universe where there aren't any stars. It turns out that we have now learned how to do that. We can look at light from stars and from quasars shining through otherwise empty regions of the universe that are thinly dispersed with gas and dust. So you have a backlight that is shining through some primordial material that has never been processed by going through a star or through a supernova. So we can try to measure the abundances of light elements in those primordial clouds and try to compare them with the predictions of Big Bang nucleosynthesis. The good news is, I hope that you're ready for this, it works. The abundances we actually see in unspoiled parts of the universe match the predictions of Big Bang nucleosynthesis. So here's an actual plot of some data versus some theoretical curves for what the predictions of nucleosynthesis are and what we observe. We see predictions for helium-4, which we just call helium, for deuterium, helium-3, and for lithium. Now you'll notice that in this plot, it is not just a single number prediction for each element, it is a curve. There's some function, there's some parameter that is being varied to get different predictions. What is that parameter? It is the density of ordinary matter. So this plot, the set of predictions, assumes that we don't know ahead of time the number of baryons in the universe, the number of protons and neutrons. And the plot is saying that as you change the number of protons and neutrons in the universe, we will make different predictions for the amount of helium, deuterium, etc. There is a value for the number of protons and neutrons in the universe for which we get the right answer. This is how nucleosynthesis fixes the number of ordinary matter particles in the universe. If there were more baryons in the universe, if there were more protons and neutrons, you would make more helium. The production of helium would be more efficient. You would make correspondingly less deuterium, lithium, and helium-3 because you would be getting rid of it into the helium. So there's a prediction that if the helium abundance is higher, it means there are more baryons in the universe, but the deuterium abundance would be lower, and so forth. There is a concordance, there's a match between all of the observations we have and all the theoretical predictions at one specific value for the abundance of ordinary matter in the universe. That abundance is 5% of the critical density. 5% of the density you would need to explain a spatially flat universe is existing in ordinary matter, in baryons, in protons, and neutrons. So this is worth emphasizing because it's one of the very crucial building blocks on our road to understanding dark matter. We can measure the total amount of matter in the universe pretty efficiently by using things like the rotation curves of galaxies, the dynamics of clusters of galaxies. We can find that there is matter there. We can extrapolate it to the rest of the universe. In fact, we could imagine that we have missed some matter, that there's something in between galaxies and clusters, but we can't imagine that we have overestimated the amount of matter. The matter we see is certainly there. So the total amount of matter we see is something like 30% of this critical density. But nucleosynthesis provides a measurement of the total amount of ordinary matter in the universe, and it's 5%. It doesn't matter what happens to those baryons, to those protons and neutrons, after nucleosynthesis. They could get absorbed into black holes. They could collapse into brown dwarfs and other compact objects. They could be spread out in gas across the universe. They would all count in what Big Bang nucleosynthesis is sensitive to. So it doesn't matter what form the baryons take. The fact that the predictions of Big Bang nucleosynthesis agree with observations of the abundances of the light elements implies the total amount of ordinary matter in the universe is not enough to be all of the matter in the universe. Not only is there dark matter, not only is there matter that we don't see, the dark matter is not some hidden form of ordinary matter. It's some different kind of particle. That is the important implication of the success of primordial nucleosynthesis for the story of dark matter and dark energy. There are other implications that we can get from the success of nucleosynthesis. For one thing, I mentioned that the process of nucleosynthesis was, number one, strictly dependent, very, very precisely, on the expansion rate of the universe at that time, when the universe was a minute old, and number two, that the universe at that time was radiation dominated. The relevant amounts of radiation come from photons and from neutrinos. Those are the light particles that were zipping around at very, very early times, dominating the energy density of the universe. So if we changed the expansion rate of the universe by just a little bit, we would predict different things from Big Bang nucleosynthesis, and we would not get the right answer. How could you possibly change the expansion rate of the universe at different times? Well, one way is you could change the value of Newton's constant of gravity. We have a constant that appears in Einstein's equation, so it reappears in the Friedmann equation. This constant tells you how strong gravity is, how much of a gravitational field or how much curvature of space-time is created by some amount of mass. This is a constant that has been around since Isaac Newton's time. It certainly describes how gravity works here in the solar system. The success of Big Bang nucleosynthesis is telling us that it is also successfully describing gravity 1 minute after the Big Bang. Nothing dramatic has happened to change the strength of gravity. There's no reason to suspect that anything did, but now we know, based on data, that it didn't happen. Another thing we know is how much radiation there is in the universe. If there was more radiation in the universe, the Friedmann equation would tell us that back then, during nucleosynthesis, the universe would have been expanding more quickly. That would have altered the predictions of Big Bang nucleosynthesis. So, for example, if there were not just 3 different varieties of neutrinos, if there were 4 different varieties of neutrinos, if instead of 3 different families of fermions in the Standard Model, we had 4 families, that would be an extra contribution to the amount of radiation in the early universe. If there was a 4th light neutrino, the early universe would have expanded faster, things would have cooled off, and you would get less helium in contradiction to what you observe in the data. So one of the reasons why we're confident that the 3 generations of families, 3 family generations that we see in the fermions of the Standard Model are all there are, that we're not going to keep finding more and more families, is because Big Bang nucleosynthesis is inconsistent with extra kinds of neutrinos as long as those neutrinos are light in the early universe. So it's a little bit mundane when you think about nuclear physics compared to dark matter and dark energy, but you should be impressed with the success of Big Bang nucleosynthesis. We take a bunch of laws of physics, all of which we figured out over the course of the last 100 years. We're in a 14 billion year old universe, and we used these laws of physics to extrapolate back to what the universe was like 1 second after the Big Bang. We made a prediction and it became right. That prediction turned out to be true. We know what the universe was doing a tiny fraction of a minute after the Big Bang. It's like you're on a basketball court, you're standing at one end of the basketball court, and you do a hook shot with a blindfold on at the other basket on the other end, and you hit nothing but net. It's that impressive, except it's not an accident. You do it 100 times and you hit nothing but net every time. We're able to go from our knowledge in the current universe all the way back then and get the right answer. The reason why that's important for dark matter and dark energy is because dark matter and dark energy are things we don't understand. Because there are so many things we don't understand in the universe, it's crucially important to have backup for the claims that we do understand some things. The success of nucleosynthesis tells us that we do understand the basic story of the Big Bang, and we do understand the basic equations that govern the expansion of the universe. Our inference that the universe today is governed by dark matter and dark energy is buttressed by these facts. So now our job is to think about what those other things that we don't understand, the dark matter and dark energy, could possibly be.